people responding over and over. So if you respond, that's great. Then you're off the table for a little while. So who wants to give me that? What's that? What is this? E to the 2x. E to the 2x. You're adding the exponents. They have the same base, right? They have the same base. You add exponents. Okay, whoever responded there, you're out. Okay, who wants this one? What's that? It's 1. Good. How is it 1, Chris?
X minus x.
Yeah, you're adding the exponents, right? So you're doing e to the x, and you're adding to it what? Negative x, right? You're taking that exponent and adding that exponent to it. X plus e to the x is 0. E to the 0 is 1, because anything to the 0 is 1 other than 0. 0 to the 0, that's a different story. But any non-zero number to the 0 is 1. So you all okay that the middle one here goes to 1? So plus 1, right, Chris? Okay, and then this middle one, wouldn't the same thing happen? We get the same thing happen. We add the exponents, you get e to the 0, that become a 1 again, and it become plus. And then what about the last multiplication here? Be careful there. Who wants e to the negative 2x? E to the negative 2x. You're adding the exponents. You're taking negative x and you're adding negative x, you get negative 2x. Look, if you're sitting there going like, look, man, this is simple algebra. Why are you taking time on this? I just want to make sure, okay? Just want to make sure that we're all okay with this sort of stuff. Yes?
Would the e to the 2x and e to the negative 2x cancel?
Would they cancel?
I mean, the 2x and the negative 2x, would that?
They're being added together. And because they're being added together, you cannot combine them in that manner, unless they had the same exponent. So let me present it to you this way. If I had x squared plus x cubed, do they have the same base? Same base, right?
Yeah.
They have different exponents. We're adding them. You cannot combine these together, right? Same base, different exponents, can't combine with addition. Same base, different exponents, can't combine with addition. So anytime you have like questions like that in your mind, like whether or not you can do that, sometimes it's easier to just like go back to a simpler idea. And if that's the way it worked for me, at least when I was trying to figure this all out, right? Okay, so that's it. We cannot do anything more with this, can we? All right, this is it. So I'm going to put that over here. This is going to be the 1/4 in front. And that 1/4 will have to distribute through to this. So e to the 2x plus 2 plus e to the negative 2x. That's not good. E to the negative 2x. Right? That's what that is. Minus, pardon me?
That's only that part.
That's only that part. So I have minus 1/4, okay? Minus 1/4. Now I've got to do this squared, right? This squared, which is going to be very similar to this, isn't it? Except we're going to have some slight differences, right? Let's see if we can do it without having to rewrite the whole thing. These are going to be minuses now, aren't they? So does it change our first term? No, that's still that, right? But on our second multiplication, this one is positive and this one is negative, which means we should get a what here? Negative 1. And then in the middle ones, same thing. We should get a minus 1. And does it change our last one? No, because they're both negative, right? So negative times negative is positive. So really, just by kind of not having to write it all out, we know it's going to be the same thing as that, except a minus 2, right? A minus 2 there instead. Any questions? Let's distribute the 1/4 through. I get 1/4 e to the 2x plus a half. That's here to here, here to here, and then plus 1/4 e to the negative 2x. And distribute here, minus 1/4 e to the 2x. Minus and minus is plus. Plus a half, minus, a negative times positive is negative, minus 1/4 e to the negative 2x. That's just distribution through, right? And now, remember what our answer is supposed to be, right? Our answer is supposed to be what? 1, so we should see a bunch of stuff go away here. Do y'all see it all cancel out? Yeah, you should get 1 left. Let's see. We've got this one, and where is it? Here, that, right? Those two cancel each other out. And then the last one's this one, cancels with this one. And the only thing left here is positive a half plus positive a half, which is 1. So equals 1. We've verified, right? This is now the right-hand side. Right? That's the right-hand side. So we have proven the identity. All right, so that's just a good example to get you familiar with, making sure you understand what this notation means. How do you square this? Be careful when you do something like this, like what turns into 1, what doesn't, what goes together, what doesn't. So there are, just like in pre-cal, there are a ton of identities with hyperbolics. There's a bunch. The one we just proved is the third one down there, right? We just proved that one. But there's others, like the first one there, hyperbolic. If you plug sign hyperbolic, if you plug in negative x, it's the same as plugging in positive x and then changing the sign. Does anyone know what that's called when you do that? I wonder if that looks familiar to anyone. It's a property of functions. Not all functions are like that, but certain functions, when you plug in a negative value, if it's the same as plugging in positive but changing the sign, we call that a odd one. That's an odd function. So the first one is showing the property of odd, being odd. The second one is even property. And then look at that next one. 1 minus tangent hyperbolic squared x equals secant hyperbolic squared x. That's another identity. Look at that one right there. That's a double angle identity. Another double angle, or not double angle, some difference identity for cosine hyperbolic and sine hyperbolic. I'm not going to prove all of these. I don't have time to prove all of these. But in your homework, you're probably going to be asked to prove something like this. And the way you're going to do it is just like this. You start with one side, do the manipulation, turn it into the other side. Now, I will admit to you that like that one right there, sine hyperbolic of x plus y equals all that, that's not a simple problem. I mean, it's not super hard, but it's not as clean as this. This was just as long as you got the algebra right, right? It's going to turn into 1. But on that one, you've got to kind of see, you got to kind of know where you're headed to make it work out. So it's a good exercise for you to try. All right, that's it. I'm done talking about the functions. I've shown you the definitions of the 6 hyperbolic trig functions. I've shown you kind of their graphs, that they're different than the regular trig functions. I've shown you how we can manipulate them and prove some identities, right? And now we get down to business. What are their derivatives, right? That's what we want to know. What are their derivatives? Well, what would you like the derivative of sine hyperbolic to be? What would make you really happy if I told you, what? Cosine hyperbolic. Wouldn't that be nice? Because that would match what happened with sine, right? Derivative of sine is cosine. Do you think it's going to be that way considering how the graphs were so different? Seems like with the graphs being so different, that probably won't happen, right? Well, what is it? Let's see. The derivative of sine hyperbolic of x is cosine hyperbolic x. It is, all right? Could we prove that? Could we prove it? Yes, we could. Let's see how we prove this. To show you this is true, and I'm not going to prove this for all of them. I'm just going to show you for one. To prove that this is true, I'm just going to say, look, isn't this just 1/2 e to the x minus e to the negative x? That's sine hyperbolic, right? If I want to take the derivative of this, how would you take derivative of this? Well, that's a constant out front, right? So it will just come for the ride. And then in parentheses, let me take derivative of each of these individually, because there's subtraction between them. What's derivative of e to the x? Itself, right? E to the x minus minus, now what's derivative of e to the negative x? Itself times the derivative of what's up here, negative 1. So you're going to have a negative come out of this, right? But you're subtracting. So it's a double negative, isn't it? Which gives you plus. So this is going to be plus e to the negative x. And that is, by definition, what? Cosine hyperbolic. You see? So that's true. What do you think? Any questions? Cosine hyperbolic x. What would you like its derivative to be? Negative sine hyperbolic, because that's what it was when it was just cosine, right? Sorry, it's not. It's sine hyperbolic x without the negative, unfortunately. Okay, so it doesn't quite work the way it did in Cal 1 with cosine. I could prove that, right? I could go and just rewrite this, right? I could rewrite this, which is this, and I could take derivative, and we would see that it would not be, yes?
So the equation on the left, does that equal the bottom, the e to the negative x?
This was me. I pointed at this when I was saying what is the derivative of that. It's this, just to show that we get a negative 1 to come out, that's going to come with this negative and become the plus. So this is just a little, like a mental little blurb on the board. This is our answer, and this is exactly what cosine hyperbolic x is. All right, so I'm not going to go through and show the proof of all of these, but here they are. Derivative of sine hyperbolic x is cosine hyperbolic x. Hey, guess what? These are on your formula sheets, okay? In fact, if I bring up the formula sheets, maybe, where is it? They are, if you scroll down, formulas 25 through 30. There they are, all right? So you don't even have to memorize those. But there they are. Derivative of sine hyperbolic x, cosine hyperbolic x. Derivative of cosine hyperbolic x is sine hyperbolic x. Derivative of tangent hyperbolic x is secant hyperbolic x squared, and so on and so forth. I would say, moving on in this class, you're not going to need to know any of these derivatives. Once we get past, like, into Cal 2 integration, you're not going to need this. This is probably going to peek its head out more later, right? Like later in a different class. So we move on. All right, just a quick check to make sure we're understanding that now that we have these 6 new functions and we have their derivatives, that we can now start applying all the rules from Cal 1. Product rule, quotient rule, chain rule, all that. So let's do one example where I ask you to find a derivative where I give you a function that involves some sort of hyperbolic. So if y equals secant hyperbolic, oh wait, I forgot the x in front, sorry. X secant hyperbolic of e to the x, I want the derivative of this. All right, so I need a new volunteer, somebody who has not responded today. Tell me what you see. Like, what sort of rule are you going to implement to take its derivative? Product rule? Okay, with some chain. Good. So there's a product right here, right? So we're going to do the product rule, which means we're going to do, using the way that I teach my students, we're going to do derivative of this times that plus the derivative of this times this, right? When it comes to taking derivative of this, though, we're going to need to know what the derivative of secant hyperbolic is, right? And it's chain rule because we have a composition, we have another function inside. So let's do it. All right, derivative of the x first. 1 times the secant hyperbolic x, or secant hyperbolic of e to the x. Then plus, now I need the derivative of secant hyperbolic of something. So since we just learned it, right, I can scroll up. What is the derivative of secant hyperbolic of something? Negative secant hyperbolic of that something times tangent hyperbolic of that something, right? So I'm going to put here, who's my next volunteer to tell me the next line? If you've answered, you're out. I want to hear from people. Go ahead.
Okay, so negative secant hyperbolic e to the x,
Negative secant hyperbolic e to the x
tangent hyperbolic e to the x times e to the x.
times e to the x. Okay, that finishes off the derivative of this, right? It's negative secant hyperbolic of e to the x times tangent hyperbolic e to the x. I think I'm missing a parenthesis. I am. I did not put plus minus without a parenthesis because that's just bad notation. So I put all of this in parentheses. And then where did that come from?
That would be the derivative of the e to the x, which was inside.
Yeah, so after doing the chain rule, we had to eventually take derivative of what's in there, right, which is that. And there's one more thing, right?
Yes, times x.
Times x to finish off the product rule. There we go. There's our derivative. I won't clean it up. I'm just going to leave it like that. Any questions on that product rule with a little bit of chain? So remember I told you on the first day, I was like, hey, you know, we got to be good with chain and all that stuff. I mean, we have to be at a certain level with that in order for this to go well for us. If you have questions, though, I mean, you need to come to me or get help, go to the tutoring lab, get up to speed. All right, I'm moving on. We have our 6 hyperbolic trig functions, right? We have our 6 hyperbolic trig functions. We have their derivatives, and we now know that we could implement those derivatives with all the stuff we've already learned. Now, let's talk about the six new hyperbolic trig functions that are the inverses of the 6 that we just learned. So every one of those functions should have an inverse, a function that undoes it. And so we're going to want to know what are they, what's their definitions, and then what are their derivatives. I don't think I want to show it to you yet. I think I want us to, do I want to show it to you? Or do you just want to derive it? Let's derive it. Let's derive it without looking at what it is. It's on your formula sheets. The definition of the inverse is on your formula sheets, but let's see if we can derive it. This is one of my favorite exercises in Cal 2 at the beginning of the semester, because we wind up getting a problem that in my many years of teaching, I've never had a class be able to figure this out. All right? Never. So it'll be interesting. I'm still waiting for that day that one of my classes can figure this out. Maybe it's today. All right? So do you remember how to find an inverse of a function back in college algebra? If you don't, let me remind you. Let's say we had the function f of x equals 3x plus 1. Let's go simple, right? Linear function. If we wanted to find its inverse, we'd first check that when you graph this, it passes vertical and horizontal line test, right? Which it does. So now to find its inverse, the kind of technique is to first replace f of x with y, right? Replace f of x with y. Swap x and y. So everywhere you see y, put x. Everywhere you see x, put y. Does that look familiar to you all or not, what I'm doing? And then what? Solve for y. So if I solve for y, subtract 1 on both sides, divide by 3. That should be the inverse function. So the inverse function would be this. So basically what this function does is if you plug a number into this, right? Let's plug a number into this. How about 2? If we plug 2 into this, what happens? So if 2 gets sent through f, it comes out what? 7. If I send 7 through its inverse, it should go back to 2. So what happens if I plug 7 in here? You get 2, right? So that's the way inverses work, right? And this process is like the standard technique for finding inverses. So let's now use that idea, and let's look at the function f of x equals, let's just go with sine hyperbolic x. I wonder if we can find its inverse. Well, is it 1 to 1? So you need to know what the graph of this looks like to make sure that it passes vertical and horizontal line test. Does it? Do y'all remember what it looked like? Yeah, I think I have it right here, so let me show it to you. Just boom, right there. That is your sine hyperbolic, right? So that passes vertical and horizontal line test. So that should have an inverse. Okay, since it has an inverse, we're going to replace f of x with y. Right? And now I have to switch x and y. And now solve for y, right? But how are you going to solve for y? Don't tell me bring in sine hyperbolic inverse on both sides, because that's what we're trying to actually figure out. What is sine hyperbolic inverse, right? So you're not allowed to do that. So the only thing I could do to start is this. I could rewrite this like that. Isn't that the right-hand side? Right? I mean, that is the definition of the right-hand side. Okay, so this is the problem right here. I'm going to step out for a little while. I'm going to give you all about 10 minutes to see if anyone can even at least get down the right path to get to solve for y on this. I don't care if you work together, okay? Don't go looking it up on the internet or anything like that, like on your phone. That's not the point, all right? And if you have seen this before with me, then that would be cheating if you do that as well, all right? So if you have seen it with me before, then I don't want you to spoil it for everyone else. I want everyone to see if, you know. Yeah, you know what you need to try? The fact that I said no one's ever done it, don't let that discourage you. They've gotten close. They've gotten real close, but there's a critical step in there that is missed a lot. So, y'all ready? Give you 10 minutes, see if you can figure it out. Solve for y. That means you got to get y by itself on one side of the equation, right? You need to get y equals, and whatever's over here can only have x's over here, right? And you can't have any y's over here. It's just got to be y over here and x stuff, anything over here that has x's. All right, 10 minutes. I'll be back. You can talk to each other. Try something, though. Don't just sit there for 10 minutes.
So can I use the natural log to just separate this again?
Can you? It does the log work that way? Can't, if you have two terms in a log, can you somehow split it? And the answer is no.
No.
You can't, and that's the trouble. That's the big hurdle in
that's
this.
where I'm
That's
at
the
right
big hurdle. And then there's a bigger hurdle after it. So, look, good. I mean, you're getting there. You're getting there. But I think we're going to go through it. Y'all ready? You ready to see this? We're going to do some stuff that I'm be willing to bet a lot that you have not seen used this way. So, all right, I'm trying to get y by itself, right? I'm trying to get y by itself. So first thing I'm going to do is I'm going to multiply both sides by 2, just to clear out the fraction. 2x equals e to the y, right, minus e to the negative y.